Hello, my name is Yerbulat Hasanov. I'm postdoctoral scholar at ISAI, and today I will explain you the concept of bias and variance. Suppose we want to predict house price based on its floor area. First, we need to generate a dataset for machine learning. Therefore, we gather several house prices and corresponding floor areas, and then plot them on a graph. We observe that smaller houses are cheaper than bigger houses. Now, let's try to fit a function to this data so that when we are given an arbitrary floor area of a house, we could estimate its price. The ideal function would look like this, but we assume that we don't know it. This is a common case in real-world problems. Instead, we will use machine learning algorithm to approximate that function. Here, we will be solving a regression problem since the output variable price is continuous. First, we should split the data into two sets, training and test. The training set will be used to train the machine learning algorithms, and test set will be used to evaluate them, mimicking the real-world use. Our first machine learning algorithm is linear regression. It will feed a straight line to the training data. This model can be represented as follows, where P is a price, A is a floor area, and C2 0 and C2 1 are model parameters. By using this linear regression model, we can estimate the price of a house based on its area as follows. Note that the straight line is insufficiently flexible to approximate the true function, no matter how we try. The inability of a machine learning algorithm to approximate the true function is called bias. In this example, we say that our model has a high bias because it is too simple to capture the complexity of the data, thus underfitting the data. Let's also try to fit a polynomial regression model. It will fit a squiggly curve to the training data. This model can be represented as follows, where P is a price, A is a floor area, and all thetas are model parameters. D is the degree of the polynomial. We can use it to estimate a price of some arbitrary house as follows. The squiggly curve has low bias because it is flexible enough to represent the relationship between house prices and floor areas in the training data. Now, let's compare these two models. As evaluation metric, we can use the sum of the squares of the errors represented here, where pi is the ground truth price of the I sample and pi hat is corresponding predicted price using our machine learning algorithm, and n is the total number of samples. We can notice that the squiggly curve perfectly fits the training data. Finally, let's evaluate two models using the held-out test set. Obviously, the straight line is much better. Note that the squiggly curve does not generalize well on the unseen data. However, it perfectly fits the training data. Therefore, it is said to have high variance. On the other hand, the straight line's performance on unseen data is similar to the training data. Therefore, it is said to have low variance. To sum up, the straight line has high bias and low variance. On the other hand, the squiggly curve has low bias and high variance. To better understand the intuition behind the bias and variance concepts, let's look at a more general case. Specifically, let's try to fit several polynomial regression models with different degrees and compute training and test set errors. As we increase the model complexity, the training error will decrease. The test error will behave as follows. In the underfitting regime, both training and test errors will be high. It usually happens when the model is too simple. In the overfitting regime, there is a huge gap between training and test errors. This usually happens when a model is too complex. We can also create a graphical visualization of variance and bias using a bull's-eye diagram. Imagine we could repeat the whole model building process more than once. Each time we gather new data and train a new model. Due to the randomness in the underlying data sets, the resulting models will have different predictions. The models that perfectly predict the correct values will be located closer to the center, or bull's eye. As we move away from the bull's eye, the predictions get worse and worse. We will consider 4 different scenarios. The models with low bias and low variance are the best. They are insensitive to changes in the training data and have good prediction performances. The models with high bias and low variance are insensitive to the changes in the training data, but have bad prediction performances. This scenario corresponds to underfitting. The models with low bias and high variance are sensitive to the changes in the training data. Sometimes we will get a good distribution of training data, so we predict very well and close to bullseye, while sometimes our training data might be bad, resulting in poorer predictions. This scenario corresponds to overfitting. The models with high bias and high variance are sensitive to the changes in the training data and perform bad. Based on these illustrations, we can describe bias and variance as follows. Bias measures how far off in general these models' predictions are from the correct values. Variance measures how much the model's predictions vary between its different realizations. We can also define the bias variance mathematically. Assume that we want to predict output y using some input x. We assume there is a relationship between the input x and output y as follows, where e is the error term and is normally distributed with the mean 0. We can use a polynomial regression or any other machine learning technique to estimate function f hat. In this case, the expected squared prediction error at a point x is represented as follows. This error may then be decomposed into bias and variance components. The irreducible error is a noise term in the true relationship that cannot fundamentally be reduced by any model. Note that it's impossible to minimize both bias and variance simultaneously. If a model is too simple, then it might have high bias and low variance. On the other hand, if we increase the model complexity, bias is reduced and variance is increased. Therefore, it is important to find a good balance without overfitting and underfitting. How to diagnose your model in order to identify whether it has high or low bias and variance. This can be done by looking at training set and test set errors. If you have validation set, then instead of test set, you should use validation set. If training set error is very small, whereas test set is much higher, then most probably your model is overfitting to the training data. Therefore, it has low bias and high variance. If both training set and test set errors are high and close to each other, then most probably your model is having high bias and low variance. If your training set is high and the test set error is even higher, then your model most probably having high bias and high variance. Lastly, if both training set and test set errors are small, then most probably your model has low bias and low variance. How to deal with high bias and high variance. Solutions for high bias are to try bigger models. So for example, to increase number of parameters. Another solution is to train longer because it might be that your model hasn't converged yet. And another solution is to try other more complex machine learning algorithms. For example, if you are using linear regression, then you can try decision tree algorithm. Solutions for high variance are to collect more training data, or you can also apply regularization. Another solution is to try other machine learning algorithms. And in general, the strategy is first to solve the high bias problem and then focus on high variance problem.